Okay, in this model, I'm going to show you how to set up a problem to analyze the transient pumping of a well at the center of a circular aquifer. So this thin disk here is the aquifer, and the well's at the center. And to begin setting up this problem, I've started to set it up, so we'll take a look at some of the things that I've done. I imported a file that had these constants in it, and these will just be used to specify the parameters in the problem. I also included a variable that I'm calling hjacob50, and this functions like a function, and it has this expression here. This is the Jacob solution from groundwater hydrology, and we can see what that is here. The Jacob solution is written out, and this is the drawdown, or the fluid pressure in an aquifer. The pumping rate at the well is Q. The aquifer properties, hydraulic conductivity and thickness, are K and B. And then there's the hydraulic conductivity again. This is the specific storage of the aquifer, time, and the radial distance of the observation point. So we measure the hydraulic head at that radial distance. So this solution applies to the hydraulic head in the vicinity of a well after the well has been pumping for a moderate amount of time. Right at the beginning, when the well first starts to be pumped, this solution does not apply. So we'll use this solution to verify the numerical solution after we've been pumping for a while. And we'll see where that comes into play when we compare the solution to when we compare this equation to the numerical solution. Okay, so that's the Jacob solution. The geometry is set up using a cylinder of 1,000 meter radius and 20 meters thick, and that's the cylinder here. The well itself is a polygon. It's just a line. You can see it right there at the center. The top surface of this disk has been hidden, so you can see it, and it's specified here as a polygon that occurs between 2 points. So each one of those points is given as a combination of x, y, and z. So the first point is 0, 0, 0. The second point is 0, 0, 20. And so we can make a polygon that has however many points we want that will be connected using this approach by putting in the points as vectors. Okay, to specify the physics, we've used Darcy's law. These are the defaults. And to make this a transient problem, we need to go and select the storage model from the subdomain selections here. And while we're at it, we'll select a boundary condition. These are the possible boundary conditions for this problem. So we'll select the hydraulic head boundary condition, and that'll be the outside of the model. And we'll also select an edge, and we'll use a mass flux for the edge. That will be the well, this feature here. Okay, so now we have to set up the storage model. This is where we specify the properties of the problem. Density and viscosity, I think, are straightforward. The matrix property we're going to specify using hydraulic conductivity, so we need to switch that over. And the hydraulic conductivity I have here is a constant that I call K. Porosity, really, for this problem is just a nominal value. It shouldn't matter, but I'm going to use 0.1. And for the storage model, the approach that we'll use is to just specify a specific storage. And so we make a user-defined value, and I call it specific storage S sub S, just uppercase, lowercase s. But now we need to be careful here because specific storage is defined using two different unit sets. This is defining it in terms of 1 over pressure, but the constant that we used here has SS in terms of, well, it says 1 over pressure, but that is 1 times 10 to the minus 5. That should be 1 over meters. It's essentially 1 over pressure head. And that's an appropriate value for specific storage of a sand in units of 1 over meters. So what we need to do, if we use SS here, is we have to convert it. And so what we'll do is divide it by 9800. This is the unit weight of water, and that'll be in units of 9800 pascals per meter. And so that's what we'll use to convert SS, which is in units of per meter, to these units, which are the ones we need. So hydraulic head is going to be 0 around the edge of the model, and we'll set that up. The mass flux, to set this up, we need to select this point, like so, and then we need to write in the mass flux. Well, we've only specified the volumetric flux in the constant, so we need to convert the volumetric flux to a mass flux, and we do that by multiplying actually Q is a volumetric flow rate, and so the conversion is volumetric flow rate times the density of the fluid, which is what we call rho, in the constants, and that's something that we've specified. And then we also divide that by the thickness of the aquifer. So that's the conversion that gives us, that goes from a volumetric flow rate coming out of the well to a mass flux in these units. Okay, so we set these terms up, and I've already done that. And so we're ready to check out the mesh. So I'm just going to use the default settings for the mesh, see what that gives us. So it's a uniform mesh over the whole domain, and you can see we're really only having it be 1 element thick. So this is not really an optimal mesh for this problem because the action is going to happen right here around the well. So an optimal mesh would be dense around the well and then be sparser here. But for now, we'll just go ahead and use this mesh and see how well it does. If we have problems with the verification, then we might consider refining the mesh. So we're going to go and run this now, and what we need to do before we run it is set up the time of the run. So I'm going to run this for 10 to the 7th seconds. So actually what I need to do is first change the number of values as the entry method. And so then we'll have it start at 0, the simulation will start at 0, and it will end at 1 e to the 7th seconds. And let's have 50 values. And so we'll use replace to change the times up here. And so that should be all that we need to do to the study, and let's go ahead and run that. Okay, looks like I forgot to fill in this part. Oh, I see. So here's something that is an easy mistake to make. I went into the storage model and I filled in all of these entries, but I forgot to select the subdomain. So we've got to make sure that we do that. And let's go, and that also applies to all of the boundary conditions as well. So we still have a problem. Let me see. Okay. So in this version, I did not in fact have a variable called rho, so we'll just add one here. So rho is the fluid density And so it's 1,000 kilograms per meter cubed. All right. Okay, so that looks good. Let's try this study again. So we go here and we run it. So it's running. Looks like we should have some results. Okay, so we can see the well, and if we go here to the end of the simulation, we see that we have some pressure change. This is just the default plot that we get as a result of running the simulation. And so the important plot that we'll generate here is a measurement of the hydraulic head 50 meters away from the pumping well, so over here someplace. And that will be what we calculated up here with this Jacob solution. It's 50 meters away because r squared is calculated right here as 50 squared. So we'll make the comparison using this 1D plot group, and I generated two graphs where they're point graphs, so they're measurements of a variable at a point as a function of time. And in the first one here, it's just this dependent variable, capital H for hydraulic head. The second one is the H Jacob 50. And the way I set this plot group up is I made the, well, let me go up here. When I set this up initially, I created in the data set node a cut point 3D. So this point is at x equals 50, y equals 0, and z equals 10. So that's a radial distance of 50 meters right at the center of the layer. And then when I set up this plot group, I have the data set cut point 3D1, and in each one of these graphs that are part of the group, I use a data set from the parent. So that will ensure that both of these are using the same information. And so here's H Jacob 50, it's plotted, and you can see two lines on here. They're quite thin, so let me just make them a bit thicker so they're easier to see. The analytical solution is green, and the numerical solution here is blue. And so they look quite similar here. They are quite similar. So these solutions are quite close. We can compare them a little bit, at least differently, perhaps better, using a log scale here. And so with a log scale, what we see is that this is the green here is the analytical, and the blue is the numerical. And we can see that at early times, there are some differences, but those differences decrease with time. And here at later times, they are really quite close. They're indistinguishable now that we made the lines a little bit thicker. Okay, so from a verification perspective, this is the behavior of this particular analytical solution. So this is, I think, a pretty good case where we can verify that this solution, this numerical solution, is working pretty well. Now, what we would do next is calculate the relative error of these two solutions and see just how well it is doing. So that's something that I'll leave for you to do. Another thing, though, that we can do with this solution is use it for numerical experiments. And numerical experiments are things that you would do to evaluate how usually it's how parameter values or some aspect of the solution affects the results. And so a straightforward numerical experiment here would be to ask yourself the question, well, what is the effect of hydraulic conductivity on this curve, the hydraulic head change in the vicinity of the well? And so one way to address that would be to conduct a numerical experiment where you run the solution several times, and just change the hydraulic conductivity. So we've set the model up nicely to do this because we have a constant here that's K. This is the hydraulic conductivity, and every place that hydraulic conductivity has appeared in the model, like in the storage model, we use this variable named K. And it also appears here in the Jacob solution, right there and right there. So if we want to change it, we change it here, and it's changed everywhere in the model. So to do our experiment, we can change it. Well, what we should do is first record the results that we have here. And I would do that by pressing this and copying the results to the clipboard. And I've made some modifications here from the defaults. I've reduced this number. I believe the default is 800, so I've reduced that to 450. That makes the graph smaller, but the fonts stay about the same size. So it ends up giving you a graph with the fonts being relatively larger, and so they're easier to read. And I also checked this box, and that will create a legend and the axis. It just makes the plot a little bit easier to read, and I also boosted the plot size. So we hit OK. We can then plot this over in Word, and I'll go over here and we'll take a look. This is that plot transferred over to Word. And so I labeled it here with the value of hydraulic conductivity, and then we can go back here to the analysis and go up to the constants, change the value of the constant here, rerun it, and copy the result back over to these places on this Word document. And so I've done that, and here's what you get. This is the analysis we just did. If we reduce the hydraulic conductivity by a factor of 10, we get this green curve and this blue curve. And here's what you get if you increase the hydraulic conductivity. Well, on first cut, it looks like the blue curves are staying the same, but that's not really true, because even though the time span here, even though this scale stays the same, this scale, this span here is much larger than this one. This is going from 0.3 to 1.8. This is minus 6 to 9. So this covers a much larger span, and so this is a much steeper slope on this semi-log plot. And if we reduce K, this span is much less than this one. So this is a much shallower slope. So that's one change. The other change that we see is in the numerical results. And when we decrease K, the numerical results are much further from the analytical solution than they are for this value of K. And the reason for that is that we recognized here in this solution that these two, that the numerical solution differed from the analytical one because the analytical one really wasn't intended to work at early time. Well, when we reduce K, the time that is, let's say, quote, early, takes much longer. So this is really at early time for the system that has a lower hydraulic conductivity. Basically, we can think of the time as being the time that's required for the pressure to propagate away from the well. And because K is much less here, it takes longer, and so we have this period here when the solutions are quite different. But you can see as we go out in time, they converge, and here at late time, they still are really quite similar. Well, if we follow that now to a K that where it's 10 times greater than this K, we can see at early times these solutions are really quite similar, much more so than either of these two. And that's really for the same reason. When K is larger, the pressure propagates out more quickly, and the system behaves as if it's progressed later in time by the time we get to this part of the plot. We also see this effect here, where the numerical solution starts to flatten out. What's happening here is the K is high enough, so by this time in the simulation, the pressure disturbance that the well has created has propagated out and interacted with the boundaries. So this is really an effect of the 1 kilometer boundary that we've put on the numerical model, which isn't included in the analytical solution. The analytical solution, the solution assumes that the aquifer is of infinite extent. So just by doing a simple experiment like this, where we have these 3 different solutions, we can learn quite a bit about the behavior of this system by comparing them and trying to understand what causes the differences in these